My name is Håkon Hoel, and I'm going to present, in total 3 works, these from 3 works, one which is a publication and 2 preprints, which are under review. All right, so this is an outline of my talk. First, I will describe the problem and summarize the results. Then I will give some details about the multi-level EnKF algorithm, tell you what it is, actually in the finite dimensional state space setting. And then at the end, I will perhaps, if time permits, say a little bit about also how one can extend the filtering IDs to the infinite dimensional state space setting. All right, so we consider a dynamics observation filtering problem, which is in discrete time. And finite dimensional state space at Z. And here is my Markov chain dynamics. So this is a hidden Markov model. And then I have these partial observations in the hidden Markov model, which are linear and which have additive noise. So there is a stochastic element in this mapping psi. So psi may be nonlinear. We have some independence relation between the different kind of random sequences. So the dynamics itself, it's assumed to be the solution of an Ito stochastic differential equation, where, well, for every simulation from time n to time n+1, the driving noise over that time interval is independent from all the previous states. All right, so our objective is for a fixed sequence of observations y hat. So this is a sequence from 1 to time n. We want to approximate the filtering distribution. So the distribution of the underlying dynamics at time n, conditional on the observations up to that time. And the challenge is, it has some different elements. So one could be that the dynamics itself is nonlinear. If it were linear, then you could employ Kalman filtering as it is. A second challenge is that even if it were nonlinear, perhaps you could sample it exactly, but let us assume that we will assume that you cannot sample it exactly, so you need to integrate this kind of dynamics using a numerical integrator, so Euler-Maruyama, for instance. Let me also say that I'm not going to use this notation, mainly y conditional y, u conditional on y equals y hat. I will just write it in this way, so in order to save some space. So this would be sort of the assumed fixed observation. Right, so let me just give you a rough idea about how EnKF works. So let's assume that we have an ensemble of particles, m in total, and they are identically distributed according to the particle filter at the updated state at time n. So this is the updated particle filter at time n. And we want to compute the prediction state at the next time of the particle filter. So how do we do it with this ensemble? Well, according to EnKF, you can do it by thinking as follows. So my approximation of the updated state at time n is the empirical measure of these particles. Now, if I want to approximate the particle filter at time, the prediction state at next time, I need to simulate each of these particles. So I need to simulate each of these particles for I equals 1 to m by integrating the dynamics one step forward. But now I introduce this parameter here because I need to do it numerically, because we assume that we cannot simulate it exactly. So I do this for each and every particle. And that's illustrated here. So here are the states of the particles. So let's assume that the x-axis here describes the state space. So it's a one-dimensional state space. And here I have a density approximation, so an empirical density approximation from all these particles at time n. Then I simulate them. So here is sort of my illustration. So you can think of time being along the y-axis. And then I have the state of the particles according to my prediction at time n here. So they have evolved from the blue locations to the red locations, and I obtain a prediction density as well. So I could have generated an empirical measure using Dirac components for each of these particles as well. All right, and now let's say that I at time n+1 obtain a new observation, which I incorporate into my full sequence of observations. Then how do I update the state of each of the prediction particles? Well, I do it one by one. So the ith particle I update, I set it equal to a linear combination of the prediction state of the particle and the new observation. It should actually be a perturbed observation here. I will return to that, but I haven't introduced it yet, so let's keep it simple for now. And then I can approximate at the end then the updated particle filter at time n+1 by my EnKF empirical measure generated from this ensemble. So I weight each particle in the same way, so a uniform weighting, and these are Dirac components then for each particle. So let me say also something about my empirical measure notation there for EnKF. So it has 2 degrees of freedom. So m is the ensemble size and n is my numerical discretization parameter in the dynamics. All right, so this was my prediction density, and what I'm illustrating in the right plot here is really the transition of the particles from the prediction state to the updated state, which is in black. So this is the prediction state in red and the updated state in black. And you see what is happening in this formula here is that each and every particle, due to this linear combination of prediction state and observation, they are somewhat attracted towards the observation, at least in this particular problem. Yeah, so that's, you see that the density itself, it actually concentrates somehow more closely to the observation. And that is one prediction update iteration in the filter. Now, let's say that we want to, and here I've used the shorthand, so y capital N, it should be equal to, it's the same as y, the sequence of observations y from 1 to n. So say that I have some quantity of interest phi, which maps from the state space dimension Rd, or it's from the state space to Rd to R, and I want to approximate this conditional expectation. Well, when I have the EnKF estimator, I can of course use that to approximate this. This is the expectation with respect to the base filter at time n. So I write this kind of a notation here. So this is a functional relating to the EnKF measure applied to my quantity of interest function. And then I have another algorithm, which I haven't really said anything about yet, but I just use this similar kind of notation here. So this is my MLEKF functional applied to my quantity of interest. And actually the MLEKF estimator is a pairwise coupled linear combination of EnKF estimators, which I will return to this, how this pairwise coupling works later. So I will not explain anything about it now. But what is the sort of core result of this paper is that if I'm looking at the reference, which we will view as being the mean field measure, so this is the mean field measure, what I denote here, so using an infinite number of samples in EnKF and no discretization error in the model, so the exact model in the simulation of the particles, so n equals capital N equals infinity, then it turns out that both algorithms, both MLEKF and EnKF, converges towards this mean field measure. And in order to achieve an accuracy of order epsilon, I need to use, it will cost me an order epsilon to the -2 using the MLEKF method, whereas for the EnKF method, the same order of accuracy costs 1 power more, so it costs me epsilon to the -3. So there are a few things to be said here. So why did I suddenly replace the base filter expectation with the mean field measure? Well, it turns out I simply did it because that's what these algorithms converges towards, and let me come back to that. There is a crime there, so let me come back to it. All right, just to say a little bit more about the notation for EnKF, but actually not so much. The way you would do it, the way I did it in the sort of animation, well, in order to do the prediction, so say that I have the particles, I have the updated state of the particles at time n. So I have them for I equals 1 to m, and its empirical measure is approximating the base filter, or the particle filter measure at that time. Well, then, in order to simulate it one step ahead, I use, I simulate each particle, and then I have the resulting empirical measure gives me an approximation of the prediction empirical base filter at time n plus 1. And then, as I denoted before or described before, in the update state, when I obtain the new observation, I update each of these prediction state particles by a linear combination. So the updated state of the particle at n plus 1 is a linear combination of the prediction state and the observation. So now I'm describing here the Kalman gain. So the Kalman gain here is a function of the prediction covariance, which is computed here. So that's a sample covariance of the prediction state particles. And then there is a further detail there as well, actually, and that's that it's not really a linear combination of the prediction state and the observations, because this is the observation, but it's perturbed observations. And if you want to look more into why that makes sense to perturb observations, you can look into our preprints, for instance, because there we cite literature on that point. Now, what should be said here is that all the particles are actually mixed because of this Kalman gain, because the Kalman gain is using information, so sample moment information from all the particles, and then they all mix and they become, so you lose the independence between the particles, which makes convergence studies more tricky. All right, so as said, we have this kind of notation that this derives from this is a functional associated to the mean field measure, and I apply it to some quantity of interest. And I can sort of take this to the limit and then talk about the mean field measure. So that's when m and n are infinite. And what we really want to study, or what we study here, is the convergence of EnKF and multilevel EnKF in this weak sense towards the mean field measure. But it should be said, as well, the crime I was talking about earlier, that wasn't really what we wanted to do. What we wanted to study was the convergence of EnKF in weak sense towards the base filter. So what I've written here, so the convergence of this thing here towards the filter here. However, that's a more complicated thing to study in the nonlinear setting, and we are simply replacing this problem by a simpler problem where we view this as the reference solution, because it turns out that EnKF converges to this thing. Now it should be said that actually we've done some numerical studies where we compare the base filter and the mean field filter in some nonlinear dynamic settings in this preprint, which I refer to here. And it turns out that in many, or at least in some settings, they are not so far apart. So it's not clear that this crime is so serious in all settings. And even if it is a crime, it gives you some partial information that you perhaps can exploit when you try to deal with the full problem, the convergence of EnKF towards this thing, or MLEKF towards the base filter. All right, so let me say a little bit now about the convergence of EnKF towards the mean field filter. So this is a result which basically has been proven in 2 steps. So the first result was by Legrand and some co-workers in 2009. So I don't present it exactly in using their assumptions, because they considered a dynamics which was not at least straightforwardly clear that could be associated to some Ito SD, but it was a nonlinear type of dynamics with additive noise that they assumed. And then we extended the result of Legrand to settings where we have dynamics which can be associated to Ito SDs. So if we have this kind of regularity assumptions, so these are basically some stability assumptions for the dynamics for whatever kind of discretization parameter. And these ensure the existence of a mean field measure. And on top of that, if we also have that there exists some parameter alpha, which we can essentially associate to the weak convergence rate of the SDE, so it enters here. Well, if you have this, if these three conditions holds, then in LP sense, LP omega sense, EnKF converges towards the mean field measure for your quantity of interest with the rates which are given here. So these are your degrees of freedom. So in terms of the ensemble size is m to the minus 1/2, which is sort of reasonable from central limit theorem arguments. And then the weak convergence rate is well expressed here in the numerical discretization parameter. And let me just note that for many SDE problems, you can fairly straightforwardly derive what the parameter alpha should be. So I'm stating one example down here. All right, so using this result, we see that asymptotically, if I want to approximate the mean field measure at some given time n for a given quantity of interest with an accuracy which is of order epsilon, then I need to choose my ensemble size to be order epsilon to -2 and my discretization parameter to be of this magnitude. Let's assume we know alpha. And then I achieve this kind of cost, and it's fairly straightforward to see that this kind of accuracy with the cost which is stated here. I just need to multiply the number of particles with the cost of simulating one of these particles. And then the transition to MLEKF will show that you can actually improve the efficiency of this kind of a method quite much by extending to the multi-level setting. All right, so I will just give you some very rough ideas of how this extension is done. So first of all, as in other multi-level approximations, we have to introduce a hierarchy of numerical solvers. So the superscript parameter here now, n, is exponentially growing parameter in terms of L. And then let us note that if I want to compute the expectation of some dynamics of some solution of an SD, some numerical solution at some fine discretization n capital L, then because of the linearity of the expectation, I can write this as a telescoping sum, what I have here on the right-hand side. And then I can think of, since I have the expectation outside of this difference, I can think of that I have a pairwise coupling of the SDs here, SD solutions at the different resolution levels. So the same driving path used at different resolution levels inside this expectation. And then I can also think that each of these expectations here I can approximate by a sample average using some number of samples, ML. So on level L, I will use ML many samples, and each of these samples are pairwise coupled, so they are sharing the same driving noise, but at different resolution levels. And then it turns out that if the pairwise coupling gives you some variance reduction, which means that you can use fewer and fewer samples on the higher levels, which is very good for approximating this thing, because it's precisely the higher level samples which tend to be costly in such approaches. Well, if this is a solution of an SD, then it is the higher level samples which are costly. All right, so you can improve the efficiency of this approximation from using only a single level Monte Carlo estimator of samples using this kind of discretization. So that would be sort of a plain Monte Carlo approximation. And then I'm not going to explain the details of how you transition to MLEKF from this ID, but MLEKF sort of builds on the same ideas. So what it does is that it is a pairwise coupled sum of EnKF realizations, where you have, well, essentially in this estimator you have 3 degrees of freedom, well, you have L, the final time level, so the finest resolution. Then you have the ensemble size, well, that's a vector that runs over all the levels. The ensemble size is sort of on the Lth difference here. And then you have the numerical resolution parameter here, which we already have stated, so geometric sequence typically. All right, so this is the rough ID, and then you have to figure out how well you can sort of exploit the variance reduction, which is introduced to the pairwise coupling of the driving noise. On top of the driving noise, there are also other kinds of pairwise coupling here. So also the perturbed observations is some form of pairwise coupling. And on top of that, all the particles on the different resolutions are actually updated using the same Kalman gain here. So it's a Kalman gain which is obtained from the particles on all levels. So this is explained in some detail here, but I'm not going through it due to the time limitations. All right, let me just shortly say here that if we add to the assumptions we had in EnKF, that we also have some sort of, that it holds that the pairwise coupling satisfies this condition which I have here, then it turns out that I can find this kind of a sequence of ensemble size ML from a MLEKF estimator and a final level capital L, such that my resulting MLEKF estimator in LP sense approximates the mean field measure for some quantity of interest up to an accuracy order epsilon at the cost which is given here. And the point here being, you can study it perhaps in detail more yourself, that the cost very explicitly relates to this parameter beta. So beta itself relates to what is classically the variance decay parameter in multilevel Monte Carlo. And the second point here, I guess, is that if you look at the cost there, even in the worst case setting where beta is not so large, it turns out to be an asymptotic improvement of the cost estimate you would have for EnKF for the EnKF method. I should also say here that this kind of log term that we obtain here, we obtain the one which is marked in red. We don't observe numerically, and we assume that it's because our proofs are non-optimally constructed. And on that note, let me say that in this preprint here, we consider actually a new form of MLEKF. I will call it MLEKF 20 later. And well, the slight difference here is that we construct the sort of the pairwise coupling of the MLEKF estimators. They don't share the same Kalman gain in this approach. And we believe that this actually has some nice properties also for extension to multi-index Monte Carlo combined with EnKF that we are working on at the moment. So for this particular one, it's this approach. As said, we were able to sort of improve the theoretical cost results also. So you can look in that preprint. We don't have this term basically, but the results are not completely analogous. So it's the regularity assumptions are actually slightly different as well in that case. All right, so let me just illustrate the performance of these MLEKF estimators for one particular example. So this is a double well SDE example. So we have some additive Gaussian noise in this particular example, and here we have the potential, say, and here we have the observations for the problem. We use Milstein numerical integration because we have a constant diffusion coefficient, so it's the same as Euler-Moriyama. And just to illustrate, so here is the potential function, and the point being here is that we want to study really how well we can infer the state of a particle just from our noisy observations, because you see that these are like pseudo stable states. So from time to time you're transitioning from one state to the other, but then you remain in one well for a quite long time. All right, so here is a root mean square error versus runtime plot for the 3 algorithms I've mentioned up to now. So this solid bulleted line, this is the performance of EnKF, and if you study it a bit, you will see that so the root mean square error is really the L2 convergence rate of EnKF towards the mean field filter for this kind of quantity of interest. And if you study it, you will see that it has a convergence of the order given here. So runtime to the -1/3. Whereas for both MLEKF algorithms, so this is the MLEKF algorithm from 2016, whereas this is the latest I mentioned on the previous slide, they have the same kind of rate behavior. So both of them seem to converge with runtime to the -1/2 order. So more efficient than EnKF, both of these. All right, so then I see that I don't really have time to talk about filtering in infinite dimensional state space, but I will include the slides anyway. So let me just shortly say that the idea, the basic idea for extension is that you have your ensemble size in your multi-level estimator, you have your time discretization, and now you also have your spatial discretization parameter that you have to take into account. And of course this complicates things, but I refer to this paper here if you are interested. All right, so to summarize then, we have presented different ideas for combining multilevel Monte Carlo with ensemble Kalman filtering. And the result of these ideas is that we have produced some methods which both theoretically and in numerical experiments are shown to outperform the single level EnKF or the plane EnKF in the large ensemble limit. So it's sort of an asymptotic study in the large ensemble limit. So convergence towards the mean field measure.